Hello, welcome to the Dynamic webinar series 2021. My name is Adriano Fabro, and this is the third day of presentations of this webinar series. Okay, just for you to catch up with our schedule of the week, we had two previous presentations on Monday and Tuesday, which are available on our YouTube channel. You can follow it again or see it for the first time. Tomorrow, we're gonna have one section on COVID dynamics, and then we're gonna start to have our short courses, which we're gonna be giving in Portuguese language, okay? Until Friday morning and afternoon, which we end our webinar series with the second short course, okay? So today we have our presentation T3, which is going to be introduced by Professor Ilmar Santos. Okay, so Professor Ilmar.
So thank you very much. It's my pleasure being here with all of you. I would like to thank for the invitation, for being the chair of the session. And it's a big pleasure for me to introduce Professor Katia Cavalca. Yeah, I mean, most of you that is used to come to Dynamic are used to meet her. But here, a short introduction to Professor Katia Lucchesi Cavalca. She's a full professor at Campinas University, the Faculty of Mechanical Engineering. She graduated in Mechanical Engineering from the University of Paulista Júlio de Mesquita Filho in 85. Completed her master's degree in mechanical engineering at Campinas University in 88, and her PhD in applied mechanics at the Politecnico di Milano in Italy in 93. Her experience in mechanical engineering involves the areas of knowledge in dynamics and machinery design on the topics related to rotor dynamics, lubricated bearings, modeling, and vibration analysis in rotating machinery. Her research program emphasizes complete system modeling applied to dynamic and stability analysis, critical components fault models for detection and identification, experimental and practical applications of numerical models in laboratory and industrial plants. So it's my pleasure to let the floor to Professor Katia. Yeah, please.
Thank you. Thank you very much, Professor Ilmar Santos. I am very glad to be here. I would like to thank the invitation, and I'd like to thank for your kind presentation as well. Thank you very much. Thank you for all of you. Are we ready?
Yes.
Mm-hmm.
My presentation today is about the impacts of model reduction and dynamic matrix extraction applied to rotating machines. Rotor dynamics has been related with several different research areas like control design, health monitoring, fault identification, and uncertainties analysis. Consequently, low-order models became mandatory, very relevant in this field of research. So, we will start with some techniques for reduction of parts of rotor dynamics machines and rotating machines, and then a review about the most used methods in reducing model reduction. Static or Guyan technique, SEREP technique, and modified SEREP technique. And then we will discuss a set of practical recommendations, highlighting some points that allow to increase the reduction success techniques of such techniques. Basically, I am going to briefly describe the rotor model, yeah, by finite elements. We have some well-known components that are discretized in this methodology. We have here a disk element, usually used to represent gears and blade sets, rotors, big rotors. And this component has 4 degrees of freedom because it's considered as a rigid component, lumped component. And it has practically 2 translations and 2 rotations around this axis, okay? And we have the translation mass matrix, the rotation mass matrix, and gyroscopic matrix, okay, related to acceleration and velocity of this component. And here we have the applied forces on it. Instead, we have the Timoshenko beam elements used to describe the shaft itself, and it's composed by 2 nodes with 4 degrees of freedom each. So a complete Timoshenko beam element is composed by 8 degrees of freedom, 4 translations, 2 translations per node, and 4 rotations, 2 rotations per node around the Y and Z axis. In this case, we can approach damping matrix as a proportional damping, which means proportional to mass and stiffness matrices. And also in this case, we have translation and rotation mass matrix. We have the damping matrix, gyroscopic matrix, and finally the stiffness matrix related to acceleration, velocity, and displacements of the beam nodes, coordinates. And here we have the applied external forces. Another fundamental component in rotating systems are the journal bearings or hydrodynamic lubricated journal bearings. The solution of this nonlinear, generally nonlinear, and obtained by numerical solution of the Reynolds equation, okay? You can get this numerical solution by finite differences, finite volume methods, or finite element methods. We here usually applies the finite volume method developed by Patankar according to the Maliska method in his book. Okay, however, this kind of components allow some linearization depending on the machine interaction between rotor and bearing. So depending on the behavior of the rotor inside the bearing, you can get some linearization of the hydrodynamic forces as proposed by Lund. Then you can represent your lubricant film between the bearing walls and the shaft surface. Here we have the lubricant oil, okay? And it can be represented by a set of stiffness and damping, or better, it can be represented by springs and dampers distributed around the shaft. And then your hydrodynamic forces depend on a term related to equilibrium position of the shaft inside the bearing, stiffness that have direct and cross-coupled coefficients, as well as damping direct and cross-coupled coefficients. So, equilibrium position, if you have only a vertical load applied on the bearing, obviously the resultant hydrodynamic force in the bearing in horizontal direction must be null, and the vertical component must equilibrate the static load on the bearing. Also, the linearization can be obtained by a finite difference, okay, in a central finite difference. Another important and crucial component that's not a rotating component, but it's crucial in the modeling of rotating systems is the foundation. It's composed by metallic parts, usually connected to other, these metallic parts can be of different materials, and usually they are connected to concrete parts, okay? So it's positioned and fixed on inertial system, inertial structure, okay? And even if we can do a very detailed model analysis of this structure and even obtain this flexibility matrix as showed here, okay, that is the inverse matrix of the impedance matrix, okay, with mass, damping, and stiffness characteristics of the foundation, okay. The degrees of freedom that can be sensing by the bearings, mainly the oil film into the bearings, okay, are the translation degrees of freedom. Because in this case, we treat mainly with short and finite bearings and not so much with long bearings. So the bearings can view or sense mainly the translation of the structure regarding the shaft position. And this must be transferred to the rotating system because it is an important influence on its dynamics response. So we have for the foundation, okay, mainly these nodes, connecting points between foundation and shaft, which means bearing position nodes, and we consider translation degrees of freedom, displacements of the foundation in the corresponding nodes to the bearings, okay? So that's my displacement vector for the foundation representation. And here we have the equation of motion and also the response and external excitation. That's considered an harmonic external excitation because it comes from the shaft vibration. Well, in this case, if you have a low number of bearings, it's not difficult to identify a number of modes, structural modes for the foundation equal to the number of degrees of freedom, and then obtain easily inversible impedance matrix. However, when you have lots of bearings, a greater number of bearings, several rotors assembled in series, you can have some problems in identifying so many foundation modes as the degrees of freedom related to the bearings. Practically the double of the number of the bearings. So in this case, it's interesting to apply the modal coordinates for the foundation. And here it's a very well-known approach, okay, by the modal matrix. These are physical coordinates and these are modal coordinates. And the main contribution of writing the foundation in modal coordinates is to get uncoupled equations of motions of 1 degree of freedom each, one for each identified mode of the foundation. And here is the transformation for the external forces, harmonic force applied through the bearings. Okay, here is the equation of motion, and here we have finally the flexibility matrix, also in modal coordinates. Okay, and the modal matrix is composed by vectors that contain the coordinates of each identified mode of the foundation. So we have this transformation. When the transformation, for example, the modal mass is normalized regarding the mass, we have these matrices are all diagonal matrices, and when we have this normalization, we have for modal mass the identity matrix, okay, and then we have the damping modal matrix, and the stiffness modal matrix has in its main diagonal the quadratic of the natural frequencies of the foundation. So how many modes you identify, how many coordinates you will have, how many modal coordinates you have, and these modal coordinates define the degrees of freedom of your foundation. So there is no necessity to identify a number of modes that equal to the number of degrees of freedom related to the bearings, the number of bearings. So it's interesting to use, and it's already a reduced mode of the foundation. A very important step here to get the reduced model of the entire system. It's the first point to get this reduction of the rotating system. Okay, here we have a schematic of a rotor bearing foundation system, complete system, okay? Then, initially, we split this complete system in two subsystems, rotor bearing subsystem and foundation bearing subsystem. Here we can clearly see the action and reaction forces that goes from the shaft to the foundation and then excite the foundation that returns vibration through the oil film of the bearing from the foundation to the rotor. Here we have the representation by springs and dampers, the linearized representation of the oil film of the bearings. And here we can see, so the rotor subsystem and the foundation subsystem, the inertial test rig, okay? And the main coordinates and axial coordinate X, vertical coordinates Z, and horizontal coordinate Y. Rotor equation of motion. The mass, here we have translation and rotation mass matrix. the proportional damping matrix, gyroscopic matrix, and stiffness matrix. The rotor coordinates acceleration, velocity, and displacement. Here we have the external forces acting on the rotor itself. Mainly here we will consider unbalance, the most common and always present in the rotating system. And here we have the hydrodynamic bearings. Now for the foundation, we have the mass matrix, the damping matrix, and the stiffness matrix, okay? And also the coordinates related to foundation. And let's remember that here we have 4 degrees of freedom for node in finite elements, okay? And 2 translations and 2 rotations. And we have bin elements and disk elements. Here we have 2 degrees of freedom per node, connecting points that are related to the bearings, okay? Only translation degrees of freedom. And here I have, we have the hydrodynamic forces, action reaction transmitted to the foundation, okay? From the rotor to the foundation through the bearings, and here foundation to rotor through the bearings. These are action and reaction. So these forces are equal and different in signal only, okay? These are action and reaction forces transmitted from rotor to foundation, foundation to rotor through the bearings. And here, eventual external forces acting on the foundation that won't be considered here in this analysis initially, okay? The objective here is to obtain a unique equation of motion for the complete system rotor bearings foundation. So we must represent the stiffness and analogously the damping matrix with the translational coefficients, linearized coefficients of the bearings, which means direct and cross-coupled coefficients, in both cases, stiffness and damping. And we have to connect reaction, action and reaction force through these coefficients matrices. So we have actually relative displacements between rotor and foundation and between foundation and rotor. So when we assemble these coefficients in this way to represent the action and reaction forces, okay, involving displacements of the rotor translational coordinates and foundation translational coordinates, as well as their velocities, okay, and then we can relate these action and reaction forces to the equations of motions, rotor and foundation equations of motions. And then we can substitute the foundation equation of motion in terms of the reaction forces and obtain a unique equation of motion for the entire system. After incorporating the respective stiffness and damping coefficients of the linearized oil film of the bearings, we can obtain a unique equation of motion of the complete system. Its physical coordinates or Cartesian coordinates, 2 translations and 2 rotations coordinates per node in the rotor system, and 2 translational coordinates in the foundation system. And then we have mass, damping, stiffness, coefficients. This is not exactly damping, it's a velocity-dependent matrix and the stiffness coefficients. And here we have external forces acting directly on the rotor and acting directly on the foundation. However, here we will consider these external forces acting on the foundation completely null. So we work only with unbalanced effects. The matrices mass, stiffness, and velocity-dependent matrix are expanded now, containing the rotor inertia, mass matrix, translation and rotation, foundation inertia, okay, translation inertia. The oil film inertia is completely neglected. And stiffness, we have rotor stiffness, foundation stiffness, and here we have the relative motion correlated here by the bearings stiffness, and here for action and reaction forces acting from the rotor to the foundation and back to the foundation to the rotor. From the foundation to the rotor. Here, it's analogous to the stiffness case, with the exception that here we have the same for the foundation and the bearing forces, but we also have here the gyroscopic effect on the rotor only. Okay, so these matrices contain the entire modeling of the system, rotor, bearings, foundation. And on these matrices now, we are going to reduce the model, the finite element model of the rotor, with the objective of control, design, application, fault detection, uncertainties analysis, and so on. Because the foundation will be reduced, properly reduced by the modal coordinates, as we previously saw. Okay, we are going through this, and then we will apply the reduction models to the rotor. Continuing from here, we have the modal approach for the foundation coordinates, physical coordinates, and external forces through the modal matrices. So here we have the generalized forces, modal coordinates, and also the relation between physical and modal coordinates to be applied in the equations, in the general equation of motion of the entire system. And then we will obtain this equation of motion in mixed coordinates, because they are physical coordinates related to the rotor, okay? And these are Cartesian coordinates to translations and to rotations. And then here we have modal coordinates that are related to the number of identified modes to the foundation, okay? The external generalized forces here will be null. We don't have external forces acting on the foundation, only transmitted forces by the bearings that are included here, as we can see by the stiffness and damping coefficients, equivalent coefficients to the lubricant film of the bearings. So we have the rotor stiffness matrix and damping matrix, okay, and the in Cartesian coordinates, and then here we have the gyroscopic matrix as well, no changes here, and then we incorporated the oil film in the rotor coordinates, physical coordinates, but the relative motion between rotor and foundation must involve the modal coordinates related to the physical coordinates of the foundation. And this involves some transformation matrices, okay? Transformation of bearings and foundation oil film matrices. This transformation is partial, and this here is complete, because here we have only modal coordinates. So modal coordinates of the foundation, the transformation, mass, stiffness, and metric and damping matrices of the foundation are here. And these are the matrices, the oil film matrices for the linearized coefficients that are partially transformed here by the modal matrix, and it's transposed, and completely transformed here in modal coordinates when incorporated to the foundation, obviously. So my new matrices, mixed coordinate matrices of the complete system with the foundation reduction to the only modal coordinates related to the identified modes of the foundation is complete here, Now we are going to see how to reduce the rotor system, okay? Because we have a detailed finite element model to the rotor and lots of degrees of freedom, because we have 4 degrees of freedom per node, okay? Model reduction of rotating system. The objective is to provide a reduced order system, okay? Still maintain the physical interpretability and the satisfactory accuracy of the response of the complete system. We can't lose information of the system, vibrational information of the system. And the motivation is the computational savings for such kind of analysis, for example, stability analysis, real-time control strategies, and so on. Starting from static or Guyan method, also known as static because he uses only stiffness properties for his approach. It's the most used and widely applied method for reducing orders of systems. And it only accounts for the stiffness effects. So Guyan reduction assumes that inertia effects and damping effects can be neglected regarding the stiffness effects that are much more important and expressive in the system. That's why it's good for structures and a little bit limited in rotor dynamics, even if it can be used in some situations. So Guyan method basically depends on the matrices reordering, okay, according to actives and discarded degrees of freedom. So here we will take the rotor finite element model stiffness matrices and multiplied by the respective degrees of freedom displacement vectors and equal to external forces. So inertia and damping effects are completely damping and gyroscopic effects are completely disregarded. Okay. Then we reorder actives and discarded degrees of freedom, okay, here. And in function of that, we will reorder the stiffness matrices, okay? And then, as I said before, on discarded nodes, no external forces must be considered. If there is external force applied on that node, it is an active node and not a discarded node, okay? So from this line here, that's a submatrix line, okay? We can get this part of transformation matrices, Guyan transformation matrices, and from this part here, okay, we can have, so the upper matrix part of the transformation matrices. And the reduced matrices will be obtained by this transformation, applying the transformation matrices, quadratic form, quadratic transformation of mass, damping, gyroscopic, and stiffness matrix. The application actually is valid for the stiffness matrices, but it is extended to other matrices, remembering and reminding that the system should have low damping characteristics and low gyroscopic effects. It increases the capability of this reduction to be successful with respect to the complete system response. The SEREP method is also applied on structures with significant inertia effects in its dynamic response. So this method, the system equivalent reduction expansion process, uses the vibrational modes, namely the eigenvectors, from the undamped complete model to generate the transformation matrix. So we take mass matrix and stiffness matrix of the system, of the finite element model of the rotor, okay, and apply the SEREP reduction. Here we are going to pay attention to the modes, the modal vibrational modes of the rotor itself, okay? Well, initially, it's important to point out that if global matrices of a global mass and stiffness matrix are not symmetric, the complete eigenvalue problem leads to a diagonal matrix of eigenvalues here, delta, okay? And two distinct right and left eigenvectors, okay? The order of these matrices will be n, number of degrees of freedom of the finite element model of the rotor. So order n, okay? Okay, let's go ahead. Again, here, this method attempts to the inertia effects and also stiffness elasticity effects, okay? So we have here acceleration and displacements, external forces. Again, we have to select active and discarded degrees of freedom, taking into account all the recommendations that we have considered before. Then we have, obviously, the transformation matrices on the right and on the left, okay, depending on U and V respectively, and considering the active degrees of freedom and the M number of modes, rotor modes, okay? Obviously, if mass and the stiffness metrics are symmetric, these metrics are the same, okay? The transformation is applied in this form, okay? And then we have the reduced model for mass metrics, stiffness metrics, extended to damping and gyroscopic matrices, okay? It's important to highlight that if the number of discarded modes is different from the number of modes of the rotor, modes considered for the rotor modeling, we have to use the generalized inverses, must be evaluated using pseudo-inverse algorithm, okay? The main reference about this modified SEREP method is given here. Again, the transformation matrix involves the right and left eigenvectors, and we have to select A, active nodes, and D, discarded nodes. But again, these nodes must be selected between the rotor number of degrees of freedom by finite element methods and the foundation degrees of freedom given by the number of modes selected for the foundation, okay? So the M vibration modes of the entire system must involve rotor modes and foundation modes, and obviously it's interesting, it is minor than the number of degrees of freedom of rotor and foundation together, okay, as it's the reducing model. And the complete and reduced models must be quite equivalent when the number of active degrees of freedom are equal to twice the number of modes as it is written in the state space form, okay? Okay, considering the complete system equation, rotor and rotor physical coordinates or Cartesian coordinates and foundation model coordinates, we have the mass matrix, the global mass matrix, rotor and foundation, the global velocity-dependent matrix involving damping and gyroscopic effect for the rotor, damping for the foundation. It's very interesting if we consider proportional damping in both cases. It facilitates a lot when it's possible. And also the damping for the bearings. Similarly, the stiffness global matrix involves rotor, foundation, stiffness here in model coordinates, and also stiffness from the bearings. Okay, here we have external forces only applied to the rotor, and then we have the dynamic matrix involving here the transformation by the mass matrix applied to the inverse of the mass matrix applied to the stiffness and damping and velocity dependent metrics of the entire system, and here the transformation for the external force. Giving continuity to this method, we have here the state space representation, okay, and the z vector here involves displacements in physical coordinates for the rotor, in modal coordinates for the foundation, and the corresponding velocities So we have the dynamic matrix and the external force matrix, and here the transformation matrix involving right and left eigenvectors, and also when we have regarding the relation, the degrees, the active degrees of freedom selected, and their relation with the number of modal or number of the modes selected. Okay, so the calculation here of the transformation matrix is practically the same. So maybe here it can involve a pseudo inverse as before. And here we have the transformed dynamic matrix and force related matrix, external force. The method is then rotation speed dependent, but the model reduction is completely in state space, which restricts the visualization of an equivalent mass spring damping system and even gyroscopic effects, okay, in an equivalent system. Regarding the modified SEREP, a second order system extraction for reduced state space representation was developed in the sense you can split the reduced matrix for rotor, bearings, and foundation. This can be very interesting, as you can you have already the reduced model of the foundation, and you can reduce the rotor model only once, okay? Instead, in the state space, you have to process the entire system reduction at each rotation speed. So it's interesting to decoupling these components again for some particular cases of analysis. For example, time domain analysis, non-linear analysis, when you need to, you would like to see the physical correspondent system matrices separately. The main conditions to matrix extraction are the complete dynamic matrix must be the sum of rotor, bearing, and foundation dynamic. And the active degrees of freedom number must be even. So we have this situation. We can obtain by state of the complete system and the three dynamic matrix separately. And again, we can going back from this representation here, we have to test this in the complete system first, and then we can go ahead with the partial reduction of each system once we have the complete reduction. From the complete reduction of the rotor bearing foundation system, we get this matrix here, and when this and with this matrix here, we can obtain the partial, the reduction. For example, from the foundation here, the terms of the complete dynamic matrix, reduced matrix, we can obtain the reduction for the bearings, stiffness, and damping, because this is known, okay? And the same for the rotor. We can identify in each part of the dynamic reduced matrix the relation and use this this reduced mass matrix here, clearly identified on the external forces, we can use to identify stiffness for the foundation, for the bearings stiffness and damping, and for the rotor stiffness and damping. Okay, so, and in this case, we can state a reduced second order equation of motion for an equivalent reduced system. Okay, now let's go to apply the theory previously discussed in a simple Jeff-Cott level rotor. Considers these dimensions, proportional damping to stiffness matrix, hydrodynamic journal bearings with these dimensions here, and the shaft length, diameter, rigid disc. Okay, and the first critical speed of the system is 53.8 Hertz. Okay, going ahead. Flexible foundation. We have an experimental flexible foundation. It's a flexible plate here, and the bearings and the rotor we simulated before are just here, placed here, okay, in the left end of the foundation. So here we have axial, horizontal, and vertical Cartesian coordinates, okay? Some dimensions of the foundation, just to be clear, 12 millimeters here of thickness, okay? This thickness here, and 1.18 meters here, and 0.29 meters here, okay? So hollow pillars are these ones, okay? It's connected in the four extremities of the plate, okay? And here we have some measurements in the accelerometer. This 7 accelerometer is placed here. So on node 12 in Z direction here, okay? And then we have amplitude and phase, the first, second, and third mode of the foundation separately, okay? So here we proceed with a model analysis, an experimental model analysis of the foundation, and got these values here. Now, first step, to put the foundation into the rotor model by model coordinates. Here again, it's the first flexible mode. Here we have torsional mode of the foundation. It's not very expressive. This is much prettier expressive. And here we have the second bending mode of the foundation, okay? Also more expressive than the second, the torsional mode. Okay. We analyzed the modes below 100 Hertz because it's the range, the frequency range of the rotor. Okay, here we can see the FRFs and also in directional coordinates forward and backward without foundation, amplitude and phase. The rotation speed is above the critical speed of the rotor, and here with the foundation effect. So it's clear, we can clearly see here the first and second critical speed, and rotation speed is also clear, okay? First critical speed is quite clear here, forward, backward, and we can see that forward response prevails in the system without foundation, okay, in the entire frequency range. Okay, and when we take the foundation into account, we can see expressive changes in both response, frequency response, and directional frequency response of the rotor at the same rotation speed. And here we can see some foundation. You can see the shaft and foundation response in forward and backward, and you can see the backward response increase due to the foundation associated with hydrodynamic bearings and isotropy. Okay, we have isotropy to the rotor, but an isotropy coming from the bearings, not so strong, but strongly coming from the structure. Okay, so that's the main importance here to analyze the foundation effects. The foundation was taken into account in modal coordinates only. Okay, so it's interesting to see here at least two foundation modes, very expressive. Yes, the rotation speed here, and the foundation modes at 37 and 82 hertz approximately. Finally, just to highlight the foundation effect on the rotor dynamic response, here we have the Campbell diagram of the rotor itself without foundation, rotor bearing system. Here we have the rigid modes of to the bearings flexibility, rigid modes of the rotor, and here the bending mode, the first bending mode, backward and forward of the rotor system, the frequency, the critical speed, okay, and the low gyroscopic effect here. Now, when including foundation, we can see the three foundation modes not dependent on the rotation speed, and it also splits the first bending mode of the rotor here, creating two very close backward and forward critical speeds, okay? And then here we can see when exciting the first, second, and third mode, this practically did not appear. It's too damped. It's a too damped mode, and it practically does not participate of the rotor frequency response, but we have these two, as we said before, and we had the rotating speed that also appears in the frequency response function and directional frequency response function. So now we are going to analyze the reduction model for the complete system once we could observe the foundation influence in a most challenging rotor with higher gyroscopic effect. Now we are going to put some reinforcement here on the foundation to minimize the vibration amplitudes, because we are going to test a different rotor with an expressive inertia and gyroscopic effect. So we will consider 76 degrees of freedom to the rotor, and 3 modal degrees of freedom for the foundation, which means 79 mixed degrees of freedom for the entire system, rotor and foundation, okay? The reduced model by all methods presented here will consider 9 mixed DOFs, degrees of freedom, okay? Around 11% of the complete model representation. So we will take 6 degrees of freedom to the rotor, 2 translations related to the bearings, and 2 translations at the disk, okay? And the foundation, obviously, the 3 degrees of freedom relate to the identified modes of the foundation. So here we can observe a very interesting Campbell diagram with first and second model, bending models of the rotor with a strong and expressive gyroscopic effect. So one time the velocity, the rotation frequency, here the natural frequencies, and these are due to the bearings flexibility, these 2 modes here, mainly due to the bearings flexibility. So consider as rigid modes, conical and cylindrical of the rotor itself. So when applying the foundation, we can also see first and second mode, backward and forward for the rotor. We can see the modes due to the bearing flexibility, and we can clearly see also first, we can clearly also see the 1, 2, 3 foundation modes. So it's a very interesting to observe that the foundation also increase the number of modes of the system and practically duplicates its and also generate more modes of the system, okay? Let's go ahead now and see some frequency response functions to observe the influence of all this coupling and also mainly the reduction procedures we presented here. Here it's clear that we have the modified SEREP in steady state. We have the modified SEREP by matrix extraction, the SEREP and Guyan method. See that at high frequencies, both SEREP and Guyan loses the accuracy. And with SEREP particularly, it can happen even in low rotation frequencies, okay? Now looking at the Campbell diagram, the modes related to the bearing flexibility, first and second bearing, backward and forward, first bending mode of the rotor, backward and forward, second bend mode of the rotor. We can see that SEREP and Guyan methods can lose accuracy in these modes related to the bearings and rotor itself. And here in the highest, the second bending mode of the rotor, they are not even capable of represent the Campbell diagram correctly, okay? Well, considering here the foundation modes, they are also, all methods as expected are capable of representing the foundation, because the foundation is not velocity dependent on the rotation speed. However, you can see that even for high modes of the foundation, they can lose, also can lose accuracy. in this, here we will analyze some computational costs. 100 speeds of rotation between 1 Hertz and 100 Hertz were equally analyzed by complete and reduced models. Okay, and then we have frequency response function, frequency, natural frequency, and damping factor and Campbell diagram. Time, this is the standard, the reference, 100% of time. And here the percentage of this time regarding the each reducing methods. We can see even that the modified SEREP takes a greater time than the other methods. His precision, his accuracy compensates this, because this is a considerable reduction regarding the complete model of the system. So, I'd like to thank you very much for your kind attention. It was a very great pleasure and honor for me to participate in this webinar, and I'd like to thank also all our research funds, FAPESP and CNPq, and also would like to thank my institution, UNICAMP. Thank you very much for your attention.
Thank you very much, Katia, for your presentation. And now we have some questions, and here, I mean, we have at the moment 3 questions that I would like to mention. The first one is coming from Marcela Machado, and Marcela says, thanks for the nice lecture. And then the question is any error associated with the model reduction in the final response? If yes, how could we be estimated and or reduced?
Let me see if I understood the question. If you have this error in the end of model reduction, would you like to extend it?
Yes.
But you don't have the complete model. Well, you can maybe extend some uncertainty propagation, but if you don't have the complete model, it's quite difficult to estimate the error of your reduction model. If you have a practical problem, you have to use, because sometimes it's impossible to process in the complete system. I can give you an example for in the stability analysis for rotor-dynamic systems. You have to approach for each step, each frequency, you have to find a stabilization situation. So, and you have to process for each step, you have to process the entire system with all degrees of freedom that obviously will be greater than the systems I presented here. So you have no choice. Sometimes you have to live with it. And it does not make sense to have a complete model and then analyze with a complete model to then analyze with reduced model, because the objective of the reduced model is to make the analysis faster. So sometimes you can't exactly know the error, but you know that at high frequencies, if you are not using the modified SEREP, you will be probability of errors is greater, considerably greater.
So thank you. And the next question comes from Adriano Todorivich Fabro. And Adriano is the foundation modes you have taken into account are low order and very global, with important effects on the rotor system. Can you say that the higher frequency modes with more complex shapes have a similar effect? If so, if it's a guideline for design the foundation, it is aspect at least.
Yes, yes. It's exactly that. The point is exactly that. For example, if you have turbochargers that work at very high rotation speeds, you can see that this foundation effect and reduction of the model is applied just in a previous phase for design, for example. Yes.
Good. Then we have also another question from André Brandão. In rotordynamic analysis in industrial machinery, we usually consider the foundation to be a simple 1 degree of freedom system, neglecting higher modes. When would you say that it is a poor approximation? Would it depending on the foundation, or does the mode shapes also play a role in influencing the rotordynamics?
Well, first of all, it's very risky to consider the foundation this way. Yeah, I think Ilmar agrees with me. But
yeah, completely.
But yeah, I think maybe a model analysis, it can be an experimental model analysis or an operational model analysis, could indicate to you if you actually have only a simple mode of the foundation, in this case, maybe a rigid mode of the foundation in the range frequency of your rotor. But you need the sensitivity, because other way you are neglected important effects, dynamic effects in your rotor dynamics measurements. You will have the effects in measurements, and you never have these effects in your model. So you can take some conclusions in a wrong way. It's very risky to take this consideration, because you are considering the foundation like a rigid block with only 1 degree of freedom. That's it's not the most common situation in rotor dynamics.
Just a small comment, because sometimes you have also some small examples where we have the rotor and you have also the spring mass system attached to some points for representing the foundation. That is also another thing that is quite difficult to represent precisely. Yeah, because normally the nodes are the foundation are connected to each other, and then when you make these simple degrees of freedom, it doesn't represent the foundation at all. Yeah.
Yes. The foundation is never completely rigid. It's a rigid body. So, yeah. And mainly the flexibility close to the bearings that are transmitted to the rotor. That's the risk.
One interesting application that we have here in the laboratory is also when you try to control the movements of the rotor and you mount your displacement sensors in the foundation. Yeah, it means when the foundation tweets and vibrates, actually what your sensor measures is a relative movement between the foundation with the pedestal. Yeah. And if you not consider it in the controller, you get in trouble. If you not correct the C matrix.
I think we have.
I think there is. You can read as well, huh? Because I mean, the next one is from Josué Tabaki. Thank you for the informative presentation, Katia. Could you please summarize the limitations of model reduction methods in the context of rotating machinery?
Okay, mainly Guyan method you can apply when you are, for example, calculating, you have a huge rotor and you are would like to calculate, for example, the bearings loading. So you can reduce your rotor by Guyan, and it will give you a very nice approach. If you have a rotor with not so big, a shaft with not so big, large rotors in diameter, you have low gyroscopic effects. If you have low damping, you can apply only SEREP model. This is very interesting because you can reduce the rotor independent on the bearings and foundation, and then you can couple them after by mixed coordinates. The problem is when you have strong gyroscopic effect, strong inertia effects, and damping, even from bearings or structure or from another source. The problem is you have to use this modified SEREP method, and it involves the steady-state solution at each rotation speed. So you have to balance if it's convenient or not in terms of time computing, time cost computing. That's the point, mainly.
So now we have also another question from Nicolas Diaz. And Nicholas is asking here, in these systems, is there a frequency which can cause a coupling of the modes?
Yes. When you put the foundation inside when you couple the rotor bearing mode with the foundation, you have the usual rotor bearing modes, and then you have the foundation modes, but you create new modes, mixed modes between rotor and foundation. My exposition was too long, and I couldn't put some of these modes, but yes, we can create mixed modes. Yes.
So I think if there is no additional questions, I would just say thank you very much, Katia, for your presentation. Yeah, it was a pleasure seeing your presentation. Yeah, very nicely structured. And then now I'll give you the word to Adriano. Yeah, please, Adriano.
Okay, so thank you very much, Professor Katia Lucchesi and Professor Ilmar Santos. It was a brilliant presentation. I had the opportunity to see a bit of this work in the past with some with Katia, and it was.
I think there is one question here I can see, but
from Domingos. Yeah, Domingos Radius. I'm sorry, Domingos. Yeah, thank you for the nice talk, Katia. Could you develop a bit more on strategy for choosing the best mode shapes to keep the reduce the basis to keep as small as possible? Cheers.
Depending on the frequency range of the rotor, for the structure, we will have, as you could see in my presentation, the foundation is how many modes you can identify. And even in this case, we had a third mode that had a very neglectable contribution in the frequency range of the rotor. But for the rotor, it depends on this frequency range. You can have first, second, third modes inside the rotor frequency. So I think this is a nice suggestion to pick up the main modes, rotor and foundation. Foundation, you have no choice. You have to pick that ones you can experimentally identify. Yes. Now I think all questions.
Yeah, I think there is no additional questions now. Yeah, Adriano, you are back. Yeah.
Well, it's good to have more questions always.
Yeah.
Please, Adriano.
Yes.
Thank you.
Okay, I just want to close thank you again for the participation, and the presentation was really nice. I really enjoyed that, and I also think the audience enjoyed a lot given the number of questions. And I would like to remind you all as well that you can tomorrow we're going to start having our short courses in Portuguese, so we invite everyone to attend that. And we're also going to have one special section on COVID dynamics, which I'm expecting to be very interesting as well. So, and that's it. Thank you all, and stay tuned to our channel. Let me be a YouTuber here now today. Thank you very much. Bye-bye.
Thank you.
Bye-bye.
Bye-bye. Thank you.
See you. Bye.
See you. Bye.